Yesterday, we stopped at this point where we were discussing about variability, spatial and temporal variability uh, of the different hydrological processes. We stopped at this point looking at annual rainfall and depth to groundwater level. So now what we're going to do is we will discuss this idea of the hydrologic cycle. You might be familiar with this. You've probably seen uh, some kind of a cartoon or a schematic diagram showing a hydrologic. So we are going to just recreate that now. So let's see how it goes. So the usual picture kind of looks like this. I have a mountain and then something like that. Okay, so let's say this is my ocean at one end, and then so this is a kind of a cross-section view of of the land surface, right? So I have the ocean at one end, and let me try to draw the other processes in a different color, let's say. Okay, so we will start from the ocean, right? So the process that takes water out of the ocean, we can call that evaporation. Okay, oh, I forgot to draw the sun. You need the sun over here. Okay, you can say this is the first time in your life you've seen a blue color sun, but well, anyway. So you have evaporation going on. That's the classical way of starting the hydrologic cycle, is to start with evaporation. But it's a cycle you can start anywhere you want, because you have to come back to the wherever you start, right? Anyway, you can start with the clouds as your beginning point, or you can start with the ocean, or whatever it is. It's a cycle. Okay. Anyway, so the sun imparts its energy to the water in the oceans and in other water bodies, lakes, rivers, ponds, and so on. And the water escapes from there into the atmosphere in the process that we refer to as evaporation. And then once it reaches higher altitudes, it forms clouds by a process called condensation. We are not going to talk about that. Okay, so you have clouds all over the place. And then from these clouds, we have water falling down to the Earth's surface. And this process, now we will call it precipitation, Precipitation, precipitation. Okay. Now, this precipitation, strictly speaking, includes both rain and snow, right? So, because we are looking at it from the Indian perspective, we are going to focus mostly on rain. But if you were studying the same course in a different part of the world, let's say in Europe or America or Canada or so on, where snow is also a regular occurrence, then you would also be interested in understanding snow behaves and so on. But for the vast majority of India, except for maybe the Italy and so on, where you get snow, the rest of it gets snow. Like 95% of the Indian landmass does not experience any snowfall. So therefore, we are going to limit ourselves to only rainfall. We will not discuss. So when I say precipitation, I mean rain unless otherwise mentioned. Okay. Then this rain falls on the land surface. Now, not all of the rain that falls on the land surface may end up on the land surface, right? So before that happens, you might have, so let me draw some trees. Okay, so now you must have all experienced this at some point of time in your life. There's a rainfall event happening, and you don't have an umbrella or you don't have a raincoat or something like that, and it's not a very heavy rainfall event. Immediate instinct is to just go and stand under a tree so that you get some shelter from the rain. And if the rainfall is not very heavy, you can actually remain quite dry, right? Although it's raining, the the tree is able to act like a natural umbrella, right, preventing the water drop from uh, coming down and hitting you, right, and making you wet. So this process of when uh, rainfall is prevented from hitting the land surface, okay, either trees, sometimes there could be a building, right? So you have a building, you go and stand under the building, in the maybe under the building, let's say, okay, under shade or something like that. That also prevents the water from reaching the land surface. Now, this process, you might not have heard this in any other course or any other time in your life before. This process by which precipitation that's falling from the atmosphere onto the land surface is prevented from hitting the land surface is called interception. Interception. Okay. Now, I'm pretty certain that you've not heard this term in this context in the hydrological cycle. So when you talk about hydrological cycle, you'll talk about evaporation, condensation, precipitation, infiltration, and so on and so forth. But this terminology that you're hearing, probably for the first time, you're hearing it in the context of the hydrological cycle. Okay, so that's interception. Now, interception depends on the type of tree. Of course, you can imagine that, right? Depends on the shape of the leaves, right? Big, broad leaves will probably be able to intercept water, whereas narrow, thin leaves will probably not be able to intercept a lot of water. It also depends on the intensity of rainfall. If it's very, very heavy rainfall, right, it's not going to do much interception, right? The water will fall on the leaf, and then the leaf has some finite capacity to hold the water, beyond which the water just drips off the leaves. So it's probably delaying the rainfall from reaching the ground by a little bit. That's about it, right? So it depends on the size of the tree, it depends on the size of the leaves, it depends on the rainfall intensity, it depends on whether the wind is blowing, right? If the wind, if it's a very strong wind is blowing, then the leaves are getting disturbed, and that causes the water to drip off from the leaves. Okay. Anyway, so that process is also happening, right? And then let's say somehow the water, other than in the areas where the trees are covering the land surface, in the other areas the water is hitting the land surface. When that happens, the water will immediately either infiltrate. So this process is infiltration, right? So please, make a note while you're watching this. Okay, it makes sense when I'm speaking, and then later on, of course, I'm going to upload the slides and upload the videos also. But it's always useful. I've always said this. It does make a difference if you are making some notes along the way. It helps to clarify some things later on. Somehow it forms some connections in your brain. So don't ignore that aspect. Anyway, so the water might enter into the land surface through this process called filtration. Now, different people use different words to describe the same process. They may say percolation, they may say recharge, they may say infiltration, right? They may say seepage. All these words kind of indicate the same process: infiltration, percolation, recharge, seepage, and so on, right? They're all indicating the same kind of behavior, where basically water that is hitting the land surface is entering under the land surface, or basically entering into the soil, right? Or soil, or whatever natural surface is present there. Okay, it could be a rock as well, right? So the water is infiltrating into the land surface. Now, what else can happen to the rainfall that's falling from the atmosphere? It can fill the little depressions on the land surface. Okay, so there are areas, for example, on our campus, if you look at it, you have these two big ponds, right, which store a lot of water. So now these ponds only are they collecting water that falls directly into them as rainfall. Suppose I have rainfall happening on above the ponds, that water is of course entering into the ponds, but the rainfall that is occurring in the surrounding areas also fills the pond, right? So because it is a big depression in the land surface, which by gravity, water tends to go to the lowest point, right? So water, the slope of the land surface is towards the ponds. If you notice, the ponds are located at the lowest elevation on our campus. So all the water naturally by gravity flows towards the ponds and fills them. But it doesn't mean that there are not other small depressions at other places in the around the campus. So for example, you might see after every rainfall event, you will see a little bit of water which will be stagnant at different places, somewhere near your hostel. If you go to the ground, the ground opposite the indoor sports complex, you will see little puddles of water there. Now those puddles which get filled, so let's imagine this is one of those puddles which gets filled with water. This is called depression. Depression, DEPRESSION, storage. Okay, so the little depressions that are found on the land surface get filled with that rainfall. Right now, whatever I've said so far, you have observed every single one of these. You might not know the names, you might not know it's called interception, you might not know it's called depression storage, but now you have a name that you can associate with it. So the next time a rainfall event happens, you can actually see the precipitation happening. Evaporation, of course, it's invisible, but it's happening, right? And then you go and stand under a tree and shake the tree. You will whatever little drops of water are stuck on the tree are going to come down, right? So you know that that process is interception, which caused all those leaves to start storing some of those little drops of water. And then when the water falls on a dry land surface, it's infiltrating into the ground. Again, you can't see that it's infiltrating, but you can infer that it's happening. You might not be able to see it, but where is that water going? It's disappearing somewhere, so it must be going somewhere. It's going into the ground. Depression storage, you've of course seen it. And most young children, and not so long ago, all of you were young kids. When you're walking on the street, you see a little puddle of water, you go and jump into that water. Of course, your parents will be saying, don't do that, but most kids do it anyway. Okay, so I mean, my kids do it. So uh, you see a little puddle of water, you want to go and into it anyway. All right, so all of these processes that I'm talking about right now, you're all familiar with this. Okay, now I'm going to start. I mean, you're familiar with them. You might not know the names, but you know the process, right? Now, the next process that I'm going to discuss is also something that you're familiar with, you have seen, but again, you might not know the name, the specific name that we're going to use. Okay, so the water that falls on the land surface, some portion of it will infiltrate, the rest of it will just flow on the land surface. It'll just flow on the land surface in the direction of the slope, right? So it'll just flow. Wherever the slope is there, it'll just flow. Now, this process, wherever I've drawn these little arrows kind of parallel to the land surface, that process, I'm going to call it runoff. RUNOFF. Now, again, this name is used in a very loose manner. The water is running off on the land surface, for we refer to as runoff. Sometimes people will call it surface runoff. Okay, sometimes people will say overland flow, right? Because the water is flowing over the land surface, so it's also referred to as overland flow. All of these terminologies mean more or less the same thing. Okay, so there's evaporation, there's precipitation, there is interception, there is depression storage, there's infiltration, then there is runoff. Okay, now is okay, any questions until this point about all the different processes that I've described? Any questions at all? Okay, so I mean, it's fairly obvious, all of these things, but we'll just keep going ahead. Now, what happens to the water that has infiltrated into the, what is going on with this water? What happens to that? Anybody would like to give some guesses on what is happening to this infiltrated water? Anybody? Let's see who's here. Tarun, please unmute yourself, Tarun.
Yes, sir.
Yeah. What do you think happens to the water that infiltrates into the ground?
Uh, uh, I think the water gets in, like it forms the groundwater table.
Okay, it forms the
Um,
groundwater table. Okay,
you
thank you. Okay, thank you. Okay, anybody else would like to add to that? It enters into the ground, and then forms, so he's referring to it as the groundwater table. So it is becoming part of groundwater. Groundwater is any water that is present under the land surface. We refer to it as groundwater. Okay, so that's fairly seems fairly obvious. But now I'm going to ask the next question. Is groundwater stationary or does it move? So when I say move, I mean in the horizontal direction. So this infiltration is coming more or less in the vertical direction, right? The water is hitting the land surface and infiltrating vertically downwards through the soil. Now the next question is, he says it becomes part of the groundwater or water table. Now, apart from this vertical movement that brought the infiltration down to the water table, does the water below the water table, does the water move? Does it move in the horizontal direction? Does it move in the vertical direction? Does it move at all? What do you think? Anybody has thoughts on that? Does groundwater, does it move? Yes, no? Sindhu, what do you think?
So can you repeat the question?
The water under the water table,
Yeah.
does it move or is it stationary? That's the question.
They move, yeah, they move.
Okay. How do you know that?
How do I
Your answer is correct. But is there any basis for your answer? Okay, there's some
Yeah,
background noise.
maybe because of the pressure differences.
Okay, because of the pressure differences. Okay, excellent. Interesting answer. Thank you, Sindhu. You can please go back to mute. There's some background noise. Okay, so there is, remember from our earlier semesters, 2 semesters, we've had fluid mechanics and hydraulics. When does water move? Water moves when there is an energy gradient. Okay, she said pressure difference. Pressure gradient is one component of the energy gradient. In addition to pressure gradient, that there might also be a velocity gradient, there might also be elevation gradient, and because of that, water may move. The summation of these three, as you know from Bernoulli equation, the pressure head plus velocity head plus elevation head is your total head. So if the total head at one point is more than the total head at another point, then the water will move from the location where the total head is higher towards the place where the total head is lower. Okay, so the groundwater, which is under the groundwater table, also moves, right? And typically, now I'm going to let me just erase this letter that I've written, infiltration here, move it maybe a little bit. I'll just, okay, I'll write it somewhere a little bit higher. Okay, I will, okay, I'll write it here, infiltration. That's this process. Okay, so then I have the water table. I'm going to draw that like a dashed line. Okay, so this line, I'm going to call it the water table. And as you can see, this water table, the way I've drawn it, it has a slope. It's not horizontal. If it was horizontal, then that would indicate that the water level is the same everywhere, which means there's no gradient. And if there's no gradient, there's no movement. But the way I've drawn it, the water will also move. Where does it move? Well, it will move to the, so in this case, so let's say the water table is intersecting this little place over here. Okay, I've not drawn it very precisely, but anyway. So let's say there is a small river here or a small lake over here. So the groundwater will move towards the nearest surface water body, right? Groundwater will go and enter into the nearest surface water body. It could be a river, it could be a lake, it could be a wetland, right? All of these, the groundwater typically will tend to move towards that. Okay, so and when water exits from the aquifer is basically, so this portion, aquifer is basically a terminology that we use to refer to the portion a geological unit in which water is stored, right? So this water table is referring to the water that is stored under the land surface in an aquifer, which is a geological unit. So it could be sand and gravel, it could be limestone, it could be sandstone, it could be clay, it could be silt, whatever is present there. It stores the water, and that unit we will refer to as an aquifer, right? So the water can move from the aquifer to a surface water body. Sometimes it can also move from the surface water body to the aquifer. So this is now this interaction between the aquifer and the surface water body. The water is flowing from the aquifer to the surface water body. We refer to that flow as base flow, BASEFLOW. Okay, base flow is the component of water that flows into a surface water body from the groundwater. Okay, so for example, let us say you are going and looking at a river in the middle of summer. Let's say in the month of May, you go to let's say the Godavari or the Krishna or the Kaveri or whatever it is, right? Now these rivers are not fed from the snow of the Himalayas, right? That's why I'm deliberately choosing these other rivers. Now in the month of May, there's no rainfall happening, but still the water will be flowing a little bit of water will be flowing in these rivers in spite of the fact that there is no rainfall happening, right? Where is that water coming from? That water, majority of it, is coming from this base flow, which is what the aquifer is doing. Is it is supplying the water to the river through the underground aquifers, right? They are supplying the water to the surface water bodies, and that process we refer to it as base flow, which is why the river flows throughout the year. Now you can think of it as base flow is basically old rainfall, because where is this base flow coming from? Just trace that arrow backwards. This base flow that enters into the river or the lake over here, if you go back, it is infiltration. And where did infiltration come from? It came from precipitation, right? The only difference is when the rainwater falls on the land surface, the portion of water that flows immediately on the land surface, this water will also come and reach this river. Okay, suppose I have a river over here. It is getting water from direct rainfall. It is also getting water from this runoff that is coming along uh, along the direction of the slope on the land surface, and then it is also coming through this other route. The water infiltrates into the soil, and then slowly it moves into below the water table, and then it slowly moves and comes out into the river or the lake as in the form of base flow. Okay, so base flow, like I said, you can think of it as old rainwater. Okay, because to come along the land surface, the water will move rapidly, but to come as base flow, it takes weeks, months, years, sometimes even centuries. For this infiltrated water to come out here, it may take a long period of time. It might not happen instantaneously, right? So by the way, what is the forecast for rain right now in Yerpedo? Is there any rain happening right now or in the next few weeks, or has it rained in the recent last 2-3 days, 5 days, something? Start paying attention to this. Check out the weather app on your phones. See what the forecast is for the next 3-4 days. And if you see some prediction for rain, go out and observe it. Okay, of course, assuming that you don't have a class at that time. Okay, so my suggestion is just check out the rainfall forecast, and as soon as the rainfall happens, just go and observe how the water is flowing. Whatever processes I've described here is happening there in real life. So you have a living laboratory in front of your eyes where you can see almost all of these processes. Of course, you can't see base flow, it's underground, it's invisible, but other pretty much you can see most of them. You can see runoff happening, right? Whenever there's rainfall, it's just fun to watch the running off and flowing towards the ponds on campus, right? So that happens on a very short time scale. Okay, whereas base flow happens on a slightly longer time scale. Okay, but the source of water is the same. Rainfall is the ultimate source of water. It's just coming back through a different route. Okay. So now to complete the hydrologic cycle, now the same base flow can also happen from the aquifer to the ocean. It can also flow from the aquifer to the ocean. Okay, this would also be base flow. Okay, or the base flow will enter the river and then the river will flow into the ocean. So that completes the cycle. We started with the ocean, evaporation, condensation, precipitation, interception, depression storage, infiltration, runoff, base flow, and then the runoff enter or the stream or the river flows back into the ocean, and that completes the cycle. Right. So these are all the different processes. One or two processes. I'll. It's difficult to explain them on this slide. Next, I'll speak about those processes. So, any questions on this so far? Any questions at all? Okay, let's keep going on. So let me just walk through those. Whatever I wrote in the previous slide, I'm just going to write them all out again. Evaporation, precipitation. Oh, transpiration. I missed that. What is transpiration? Anybody knows what transpiration is? What is transpiration?
Water evaporation leaves.
Evaporation from the leaves. Yes. So the leaves of the trees or any vegetation that you have, in the process of photosynthesis, what do? They take carbon dioxide from the air, what is that? Sunlight, the energy, and convert that into glucose through that processes of photosynthesis. And in that reaction, they release oxygen, which goes back into the atmosphere, and moisture, H2O, which again gets released back into the atmosphere. So that process is called transpiration. That happens from all the different vegetation that you have. So it could be a forest, it could be grass, it could be crops that are growing. All of these go through this process called transpiration, which releases moisture or water vapor back into the atmosphere. Okay, I missed that in the previous slide. Anyway, then there's interception, which is the portion of what precipitation that gets intercepted by the leaves of the vegetation. Could also be a building that prevents water from reaching the land surface, but that's relatively small. Then depression storage, I already told you about. Overland flow, surface runoff. Again, these two terminologies are kind of similar, referring to the same thing. And then there's infiltration or percolation or groundwater recharge. All of these terms more or less mean the same thing. And groundwater flow or base flow, right, which goes back into the surface water body and completes the hydrologic cycle. Okay. Any questions? Any questions on any of these terminologies that I've used over here? Okay, if there are no questions, let us go ahead with, we'll talk about base flow. Let's just start. Okay. We're just going to do a simple problem which is going to help us do what is called a water budget. Okay. Whenever I look at a particular area, I want to be able to write a water budget. When I say water budget, what is the idea of a budget? You estimate all the sources of income and you estimate all the sources of expenditure and you try to balance them, right? So if you have a budget of, let's say, I'm going to receive 5,000 rupees this month and I'm going to spend 6,000 rupees this month, that means you have a deficit, right? You have an income of 5,000 and you have an expense of 6,000. That means your bank balance is going to go down by 1,000 rupees, right? If on the other hand, I have an income of 5,000 and an expense of 4,000, then my bank balance, bank balance is your storage, is going to increase by 1,000 rupees. So fairly the same thing we are going to do as a problem for in this particular numerical example. We're going to do a water budget equation. Okay, now this water budget equation can be done for anything. It can be done for for one building. It can be done for a whole campus. It can be done for the city of Tirupati. It can be done for the district of Tirupati district or Chittoor district, or it can be done for the whole of Andhra Pradesh. It can be done for one lake. You can take any unit and do water balance analysis for that, right? And write a water budget equation for that. Let's just read through this problem statement. It'll be very interesting. Okay. A lake had a water surface elevation of 103.2 meters above the datum at the beginning of a certain month. Okay, so this is like the bank balance on on the 1st of August was something 10,000 rupees, whatever it is. That's what this is telling us. The water surface elevation of the lake is like your bank balance on day 1 of the month. Okay, in that month the lake received an average inflow of 6 meter cube per second from surface runoff sources. So this is describing all the money that is coming into the bank account. Okay, you can think of it that way. In the same period, the outflow from the lake had an average value of 6.5 meter cube per second. Okay, so which means all the expenses from your bank account, that is being, some number is being assigned to it. Okay, so you have the water level at a certain elevation, some inflow is coming in and some outflow is happening at the same time. Further, in that month, the lake received a rainfall of 145 millimeters, and the evaporation from the lake surface was estimated as 6.1 centimeters. Write the water budget equation lake and calculate the water surface elevation of the lake at the end of the month. The average lake surface area can be taken as 5,000 hectares. Assume that there is no contribution to or from groundwater storage. Okay, so the first thing I'm going to do is I'm going to maybe draw a conceptual picture of this lake. So this is my lake. Okay, supposed to be a straight line. Okay, so this is my lake, and this elevation is 103.2 meters above some datum. So I have a datum at some level. Above that datum, the water surface elevation is 103.2. It is receiving an inflow of, let's call it I, equal to 6 cubic meters per second. And there is some outflow, I'll call it O, and that is 6.5 cubic meters per second. It received of 145 millimeters. So P, precipitation of 145 millimeters. Okay, and evaporation from the lake surface was estimated as 6.1 centimeter. Okay, so let me denote that E as 6.1 centimeter. Let me convert everything to millimeters so that it's convenient. 61 millimeters. Okay, write the water budget equation for the lake and calculate the water surface elevation of the lake at the end of the month. So at the beginning of the month, it was 103.2. What will it be? Will it be more than 103.2 or less than 103.2? That is the idea of the question. Okay, and then the surface area of the lake is given. It is 5,000 hectares. So 1 hectare is around 10 power 4 meters square. So now this is a very typical kind of problem, and it's the last sentence is assume that there is no contribution to or from water storage. Oh, sorry. Okay, so therefore we have accounted for all the sources and sinks. Okay, source is something that brings water to the lake. Sink is something that takes water away from the lake. Okay, so now we have all these numbers. Unfortunately, these numbers are given in some kind of mixed units. Okay, I have meter cube per second, I have millimeters, I have centimeters, I have hectares. Okay, and some things are given in as a rate, meter cube per second. Something is given as an absolute total amount, right? Precipitation of 145 millimeters. So then it becomes a challenge for us to figure out how to understand all of these different processes in a way in which an equation which accounts for all these processes and takes into account the fact that the values are given in different ways. In one case, a rate is given. So the inflow is given as so many cubic meters per second. Okay. At the same time, I'm told that so many millimeters of rainfall happened in the entire month. Okay, so I have to be able to account for all of these things and write a simple equation. Now, there are two ways of doing it. One way is to say, since I'm given one number in meter cube per second, I will convert everything to meter cube per second and write the entire equation in terms of meter cube per second. Okay, that's one way of writing it. The other way of writing it would be to say, I'm given the precipitation and evaporation in units of length. Okay, so I'll convert everything to units of length. Inflow is meters per second, but I know that my period of evaluation is 1 month. So I can convert that to so many meter cube per second, multiple of seconds in a day, multiplied by number of seconds in a month, number of days in a month, right? So that would give me the total volume of inflow and the total volume of outflow. Again, it's a problem. What is given is a volume, and here what is given is a length. How do I convert it? Anybody has thoughts?
Divided by the area.
What's divide by the area, of course. Or if you want to keep the meter cube per second, then you will take the length and multiply it by the area. That would give you meter cube as well, right? So it's, I mean, it's an involved calculation, but as long as you are doing it consistently, the problem, there's nothing fundamentally difficult about this problem. So let me just write the equation out, and then we will uh, I'll leave the calculations to you. I'll just write the equation, and then you can go about solving the actual problem. So the typical way of writing a water budget equation is to say inflow, right, minus outflow right. When I say I mean all the inflows. Okay, in this case I've already written multiple types of inflows, so let me write it like this: inflow, that is this term, minus outflow, that is this term, plus precipitation minus evaporation, okay, equal to delta S, change in storage. Okay, does that seem reasonable? Now the only catch is that either you convert all the equation to meter cube per second, or convert all the terms in this equation to meter cube, or convert all the terms in this equation to meters or millimeters, right? So you either have to do, everything should be in L cube by T minus L cube T minus 1, or L cube or L. Okay, what you choose to do is your it's up to you, the convenience, but which means that the right hand side is the unknown in the equation. That will also come out in this. If you fill all these terms in meter cube or meter cube per second, you will get change of storage per unit time. Okay, so then you'll have to convert that again. But the question is asking you what is the water surface elevation of the lake at the end of the month. So that gives you a hint that if you get this delta S as in units of meters, let's say, then you can directly take that and use that to find out what the water surface elevation will be at the end of the month. Right? So it doesn't make sense to get an answer in meter cube per second and then convert it to meters and then find out this thing. Instead of that, you just convert everything to meters and solve the whole problem. So how do I convert I to meters? I'll just talk about for 1 minute, and then the remaining terms I'll leave it to you. So it is 6 meter cube per second multiplied by 86,400 seconds per day multiplied by 30 days per month, right? So this will give me 86400 into 30. So second cancels, day cancels. So you've got meter cube per month. Okay, and then you divide this whole thing by what is it? 5,000 hectares. 5,000 into 10 to the power 4 meters square. Okay, so in the numerator I have meter cube per month divided by meter square. So I'll get an answer meter per month. Now that per month, because the duration of analysis is only 1 month, so you can just say it is the change. It is the amount of inflow that happened during that 1 month. You can just write it as meters. Similarly, for this O, you will do 6.5 into 86,400 into 30 divided by this same number. Of course, it will have a minus sign. So it will be 6 minus 6.5. Or you can directly just do minus 0.5 into this whole thing. It doesn't matter. Then this precipitation term, it's given in millimeters. So you just divide it by 1,000, you will get 0.145 meters. So that will be plus. And then evaporation will be 61 millimeters divided by 1,000 to convert to meters, but that will be minus 61 divided by 1,000. So you add all of these terms up, you will get an answer. You will get a numerical answer. Okay, now that numerical answer, you will have to make sure that, of course, the signs have to be taken care of. Let us say that answer comes to, I mean, I don't know the answer. I'm just telling you. Let us say the answer comes delta S equal to minus 0.1 meters. What does that mean? If the change in storage delta S is negative, what does it mean?
The elevation dropped in that month.
Yeah. If the delta S value turns out to be negative, that means the water surface elevation of the lake dropped. If it comes out to be positive, that means the water surface elevation has increased. And then whatever that number is, if it's minus 0.1, you take that 103.2, subtract 0.1 from it, you'll get the new elevation. If it comes out to be positive, then you just add that number 103.2 plus 0.1, whatever it is, that gives you the new water surface elevation at the end of it. Okay, so now, like I said, this idea of writing a water budget equation, it can be done for any duration of time, for any spatial domain, right? I can write the water budget equation for 1 day for one room in the hostel. Suppose you are a person who's staying in that room. I can find out how much water comes into the room, water leaves the room. Just saying, okay. I mean, you bring in two bottles of water, and then you drink half of it, and then whatever, right? So, or you wash your clothes. How much water you're using up, how much water you are drinking, how much water you're using for cooking, whatever it is. Of course, hostel, somebody else is doing your cooking, but anyway. So I can do this water budget analysis for any domain. Okay, I can fix the boundaries of the domain. As long as I know how much water is entering or leaving through those boundaries, I can do this water budget analysis for any system. It could be a lake, it could be the campus, it could be a watershed. Now, again, you might not be familiar with the term watershed. We will talk about that, in the coming lectures. Anyway, so the idea is that this concept of writing a water budget equation is something that can be done for any spatial unit of any size. There is no limitation on that. You can write a water budget equation for a soil sample, right? You just take a soil sample, look at it, and say, okay, it received so much rainfall, and then some water evaporated from the soil and went back into the atmosphere. Some of the water infiltrated and went into the ground, and so on and so forth, right? So you can do this kind of a water budget analysis for any size and for any duration. You can write this equation for 1 minute, for 1 day, for 1 year, and so on and so forth. Okay. So that's kind of like to this whole topic of the hydrologic cycle and the idea of a water budget equation. So now I'm going to just quickly move on to the next topic. I don't know if you can't see my screen, right? Okay, are you able to see my screen? Yeah, we'll just spend a little bit of time on this today. So the next topic that, okay, is my screen visible on full screen?
No, sir.
It's not full screen. It's not visible. Okay, hold on.
No, sir.
Just hold on. Just give me a second. Now it will be visible. right? Full screen.
Yes, sir.
Thank you. Okay, so now the next topic that we are going to be discussing is precipitation. Uh, so after this, we will every module that we talk about will there'll be one module completely on precipitation, one module completely on infiltration, one module on evaporation and transpiration, one module on runoff, one module on groundwater, and so on, right? So that's how the whole course goes. So we'll have about 5 or 6 modules in total. Okay, so precipitation, there are just different types of precipitation. These are some of the words that are used to describe them: rain, snow, drizzle, glaze, sleet, hail. All these different terms are used. I'll not get into the definitions of all of this. You can just look it up in any textbook. It's not very, of course, in India, as I said, predominantly we just get rain and drizzle. This glaze, sleet, hail is also a little bit common. It happens every now and then, but it's just a definition. Okay, so it's no big deal. You can memorize these things. It's not hard. Okay, in terms of the processes that deliver this precipitation to us, there are different types of names assigned to them. So there's the idea of a front, a cyclone, an anticyclone, convective precipitation, and orographic precipitation. Now again, I'll give some reading material from the textbook which defines all of these different terms. Okay, I mean, I don't expect you to memorize any of these things. We'll just talk a little bit about convective and orographic precipitation. Now, convective precipitation refers to rainfall that happens typically it happens during the summer when you have a very hot day, and what happens is when you have a hot day, the the air gets heated up on top of the land surface and rises up, and when it rises up, it creates a low pressure above the hot land surface. So the surrounding areas, if there's a water body there, because of the heat, um, mm, the water vapor is present in the air above that, and it is at a higher pressure. And so because of the low pressure created above this hot land mass, the high pressure tries to equalize the pressure, and then you get a convective current, okay, which causes the high pressure and the low pressure area above here to be get filled by the moisture laden air from the surrounding areas, and it results in a thunder shower, typically in the evening. Okay, in the summer you might have experienced this. If it gets very hot during the day, around 5:30 or 6 in the evening, you'll get a little bit of rainfall. Okay, that kind of rainfall is called convective precipitation. Okay, then this orographic precipitation typically refers to precipitation that happens when you go to a slightly higher elevation. Again, something similar happens. Um Air gets moisture gets collected in the air, and it rises up, and when it rises up, the temperature is lower, so that air cools down, and then it comes down. I mean, the condensed moisture condenses and then falls as precipitation at a higher altitude. So which is why you will see that you go to some of these hill stations, right? In the summer months, you will get some rainfall in the hill stations, because that hot air rises up, and it carries moisture with it. When it goes to the higher altitude, it cools down, condenses, and then falls. That is referred to as this orographic precipitation. Okay, I mean, I'll just share some reading material that will have all of these definitions. Okay? So the Indian monsoon, uh, where typically you have what is called a cyclone, right? A cyclone coming in and hitting the coastline. You have those, we spoke about this in the last class as well. There is the southwest monsoon, which typically lasts from around June to September. And then we have the northeast or the retreating monsoon, which is typically from October to around 15th of December or so. Okay, so that's a brief introduction to precipitation. We will stop with that for the day today, and we will resume again on Friday. Okay, in the meanwhile, I'm going to share some reading material about this precipitation. You can just look it up. I'll share it on Google Classroom, and we'll take it from there. Okay, so take care, everybody, and see you all on Friday morning at 8 a.m. Thank you very much. Ta-da.